Okay, so we started off and we said, this Monte Carlo methods class, it's, we're trying to find integrals and probability distributions, learn how to sample from probability distributions to answer these questions. Maybe we want to find the expectation of something that is described by a probabilistic phenomena, okay? And so today we're going to talk about generating random numbers that come from a certain distribution. We're going to assume that we can generate numbers on the interval 0 to 1, okay? So today we will cover random numbers from certain distributions. We'll just say from, yeah. Okay. And in particular, we will look at a method called the inverse transform method. I've decided this will be the book that we're going to use. It's available for free as a PDF through SpringerLink. Okay, you can. I've kind of finally written the syllabus, and I'll have that posted, and the link to the book will be in the syllabus. Oh, let me just explain a few things about the syllabus. So once I get the online poll thing figured out, I'll probably start taking attendance next week. We'll say attendance counts for 10% of your grade, but I'll also have these random, not really random, arbitrary audit checks, and if it doesn't line up, all right, if you're not being honest on the online poll, then you will forfeit your full 10 percentage points, okay? So just be honest. If you're honest, then you have nothing to worry about. But if you do fill out the poll and you're not present, and I happen to take actual roll call that day, you'll forfeit your 10 percentage points there. I've decided we'll have 5 homework assignments. Each will also be worth 10%. And then we'll have 3 tests in class, and they'll each be worth 12%. Okay, so so I'm trying to make the exams not crazy heavy. It's not going to be like 40% midterm, 50% final, or something like that. So we'll have 3 tests. Got the dates on the syllabus, but week 4, week 7, week 10, we'll have 3 tests, and they'll be worth 12% each. And I think that leaves 4% left over. So I wrote 4% for being awesome. Okay, so everybody will get that. Yeah. Okay. What's that?
So does that mean there's no final exam during finals week?
No. Correct. There will be no. Yes! Well, I'm glad someone's excited. Yeah, it's spring quarter. You guys are seniors, so we'll say. All right. So we'll have your third test will be during 10th week, and we'll call it a day there. Okay. I'll probably make the 5th homework assignment due sometime during 11th week, just because I know 10th week can be kind of crazy. So we'll make the last homework assignment due during finals week, 11th week, and then whenever you finish that, you're done. Okay, so that's the plan at least, right? Okay, so that'll be posted. Link to this thing available, and so this is coming from chapter 2. Chapter 1 is kind of like, do you remember everything from intro stats and R? And so I do recommend going through chapter 1. Perhaps there might be some tests in here that you have forgotten about, like the correlation test. I don't know if you ever learned a correlation test. Maybe it's basically, you've got two numeric variables and you can find correlation between them, right? And then always in statistics we ask, is this correlation for real or is it a possibility of random chance? And that's what the correlation test does. And it's really easy when you have R. You just say core.test, and there you go. Okay, so we're going to talk about the inverse transform method, where basically, we will assume we can generate values from the random distribution, random uniform distribution on the interval 0 to 1. Okay? And so we will say the random variable u capital U, I'll just write capital U, comes from the uniform distribution. All right, and I just put up a link on YouTube. It's like a 20-minute video with this crazy looking guy, but it's a great video. It just talks about how computers generate random numbers. First talking about the linear congruential generator, and then briefly talking about the Mersenne twister, which it's a little bit more complex than we need to know. But basically, when you ask the computer RUnif, it's going to give you a random variable from the uniform distribution 0, 1. Okay, so given this, what if we want to generate a random number that comes from a different distribution? Let's say the exponential distribution, or let's say we have a discrete distribution. What if we want to do that? Okay, so the uniform distribution, basically between 0 and 1, everything is equally likely, right? So our uniform distribution, it looks like this. Technically, it should have a height of 1, and the total area here is equal to 1. What does the so this is our probability density function. What does the cumulative density function look like? Exactly. So going from 0 to 1, on the horizontal axis, we go from a height of how high do we go? So at the bottom we start at 0, and at the top we go up to 1, right? And then from 0, we're at 0 here, and then is that right there? Basically, between 0 and 1, our cumulative density function increases nicely like that, and then after that, it looks like this, right? And the CDF represents what is the probability that u is less than or equal to some value u, right? So if this is the axis u, what's the probability that this random variable u is less than or equal to some, so if this is little value u right here, then this says, there's a whatever 60% probability, okay? On the PDF, it is equivalent to kind of the shaded region, right? So okay, let's we'll just start off with a super simple example. All right, let's say I've got this categorical distribution. Okay, so the categorical distribution might be written as, you know, cat 0.1, 0.3, and 0.6 or something like this, right? And so this basically means that we've got category A and the probability. Okay. And let's say I said, write a program to generate random draws from this categorical distribution. How would we do this?
You can do RUnif and then say if RUnif is in between these values, do.
Okay, so yeah, so we'll do write a function to make random draws from this distribution. All right, so we'll just say x is equal to RUnif 1, right? Or maybe I'll use our standard R code. Okay, and then what do we do? So x is in between 0 and 1. That's what we know. And then what do we do? We say if x is what? Less than 0.1, then I guess we'll say y. I'm sorry, forgive me. I'm going to say u will come from RUnif, okay? We'll say this, okay? So if u is RUnif 1, and we're going to say if u is less than 0.1, then what do we say? Then this is all pseudocode here. Then x will be given what value? A. Okay? And then what's the next if statement?
Else if.
Yeah, I guess it'll be an else if, and then we'll say basically u is greater than or equal to 0.1, and
But if you do an else if, you don't.
yeah, if you do an else if, it's not necessary to do this, right? But just to kind of signify this, but we'll do this. So and u is less than what? 0.4, right? And u is less than, and I'm going to write 0.1 plus 0.3. Then x is given the value b, and then we do an else if, or we could just do an else, but and then finally, you know, u is greater than or equal to basically, I should 0.4, and u is less than 1, okay? Then x gets assigned C, right? And obviously some of these parts here are redundant, okay? But I'm hoping, is this okay? To say, if we've got a categorical distribution and we say we can generate numbers on the interval 0 to 1, no problem, can we then generate random draws from this categorical distribution? And the answer is yes, we can, okay? That's easy. So this is no different than if instead of the categorical distribution, we just changed it up to, let's say, some other discrete distribution, like, let's say, binomial. And we'll say binomial where x is equal to 3 and p is equal to 0.5, or not x, n is equal to 3 and p is equal to 0.5, then what do we have? We have our probability mass function can be expressed as such that we have 0, 1, 2, and 3, and what is this? 0.125, 0.375, 0.375, and 0.125, right? So this would be x, and this is probability that x equals x. I hope I'm not doing this too quickly. Are we okay with this? The binomial distribution, right? You flip the coin 3 times, and we say each time you flip the coin, probability is 1/2. And then so we set up our probability mass function, which you do n choose x, p to the x, 1 minus p to the n minus x, and you get all of these values, right? Okay, and basically we would just set up the same problem, right? So write a function to make random draws from this distribution. Basically you'd say u comes from r unif 1, and then you set up kind of your if chains, okay? If, else if, if what, u is less than 0.125 or something, blah, 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 okay? Else if, and else, and then you can say x, gets assigned the value of 0, things like that, okay? And so basically we are mapping u, and so this function, we map from values of u to x. Is this okay? Okay, and so I'm going to take this and we're going to try to represent this a little bit graphically to explain what's happening. Okay. I just want to make sure. Okay, so if I let me create a graph of the PMF. Okay, and basically your PMF looks like okay, and then what does the cumulative mass function look like? Right, okay, so it's so starting at 0, at the end when we get to wait. Sorry, I gotta. Yeah, okay. We'll just start right. Okay, I gotta do some form. Okay, so at 0, it goes like this, and then this is what, 0.5 right here. It jumps up, and then it jumps up, and then it goes like this. Okay, so and we can't remember. Do the circles go over here? It's a solid and a circle and a solid and a circle and a solid and a circle, I think. Huh? Can someone just double check on Wikipedia and see the CMF? But okay, and so the idea here is, you know, until you get to 0, right? There's anything lower than 0, there's no probability, right? The cumulative mass function is 0, and then when you get to 0, then the probability, because remember, the CMF represents what's the probability that x takes on some value less than or equal to x. You know, as soon as it gets to 1, this is at a height of 0.125, and then when it gets to 1, we add this thing and we get to 0.375, and when we get to 2, we add this on and we're at 0.875, and then at 3, we're up at 1. Okay? All right. This part's okay? So we've talked about how to map from 0 and 1 to these values 0 through 3, right? We said kind of our rules. We'll say if u is less than 0.125, then x becomes 0. If, and then it'll be an else if u is less than 0.5, x becomes 1, else if u is less than 0.875, x becomes 2, and then else, which implies that, of course, u always has to be less than 1, then x becomes 3, right? Okay, and so what I can do is I can kind of shade little pieces here. This is kind of the zone for 0, and then this is the so I'll kind of just run across here, and then that goes across, and there's this kind of this sense that to go from some to go from the uniform to a discrete distribution, you can just set up is u less than or equal to you know, the probability of this value, you know, kind of between this spot and this spot, right? So what would we call 0.875, 0.5, and 0.125? Looking at all of these things, so we would say we would call each of these things so this is probability that x is equal to x, and then over here we would have kind of we would have the cumulative probability, which we will call p sub k. This is the cumulative probability, okay? And so we just say 0.125, 0.5, 0.875, and 1. And then so the way we generate for a discrete distribution, okay, so to generate we say U comes from uniform on 0, 1. We'll make this a capital U. And then we say x takes on some value k if p sub k minus 1 is less than u is less than p sub k. And that's how we generate values from a discrete distribution given random uniform. Okay, and so if you were given this task or assignment, I think it would be rather straightforward. It would be just a matter of calculating each of these and calculating the corresponding p sub k, and then all you do is you just generate a u, and then you kind of run through and you say, well, where does this fit in? Okay, and probably, if it was a binomial with here, I want to make a homework problem out of this, but I don't want to give you the answer on how you would do this, right? So let's say it was a binomial distribution and you're flipping the coin 50 times or something like that, right? So you have a total of 51 possible outcomes. You clearly don't want to write 51 else if statements or 50 else if statements, okay? So you can do a loop, and what would a simple way to, I feel like I'm giving you the answer here. But if you had to do this, how could you do this with a loop?
Nested switch statements?
Yeah, you could do a bunch of switch statements.
Oh no, nested for each loop.
For each loop, I'm trying to think.
A double for loop or triple loop?
Maybe? I don't know. I'm okay. I guess I had something in mind. You have something different in mind. Your method's probably fine, but it's hard for me to just picture this right off the fly. But you can just kind of start off with basically the question will be, is x equal to 0? And x will equal to 0 if u is less than kind of your first value, right? And then if that answer is a no, you would then go to the next iteration of the loop, which is now going to ask, is x equal to 1? Okay? And x will be equal to 1 if u is between these next two values, right? And then if the answer there is no, then you go to the next iteration of the loop, okay? And then so every time you go to the next iteration of the loop, you just have to update your x. That's easy. X is going to be x plus 1. And then you have to update kind of the boundaries of where you think x, where u has to be for x to take on that value, right? And so the boundaries will be updated basically by, your p of x things, and it kind of counts up in that way. And then you would just run through that and generate that. I don't know. Well, I don't know if I should write this down or let you wrestle with it, and I'll do a very loose pseudocode here, and then I'll give you the homework assignment to do it, right? So let's say, generate random draws binomial with n equal to 50 and, I don't know, p equal to 0.5 or something like this, right? So you're going to just start off at for I in 0 through 50, okay? And then the question is x equal to I, right? This is this is our question, is x equal to I, and x is equal to I, and then we just say if u is less than, I'm going to say p sub k, and u is greater than p sub k minus 1, then you can assign, I guess it should be p sub I and p sub I minus 1. So obviously there's a little bit of an exception when you start off with 0, okay? You must, don't forget the edge case. Okay, and if yes, then x will take on the value I, and then you will break, okay? And then else, you'll do something, okay? Basically, update the p sub I values, okay? And then you'll go to the next loop, right? Or maybe you don't even have to do next, okay? Because it will. Kind of something like this, right? This is very loose pseudocode that this will not work if you just try to go straight off of this, okay? You got to obviously think about it a little bit to get it to work. But this will generate then random draws from the binomial, and you can test out your clunky thing versus R's very efficient R binom, and do a test there. Okay, is that all right? Okay, and then well, if you're convinced that that works, then we can talk about then generating values from a continuous distribution, right? So again, we can still generate values from u01, okay? And we can do a similar mapping to generate from a continuous distribution. All right, and our favorite continuous distribution is the normal distribution, but it's hard, and that'll get its own separate lecture Friday. But we'll say let's say we're dealing with the exponential distribution. Okay, do you guys remember the exponential? All right, what the exponential distribution? The PMF is given by I need Wikipedia. It's what? Lambda times e to the negative lambda x? No. Yeah. Huh? What's that? Something along those lines, right? This is that's our entire life, right? Exponential distribution. Here it is. Lambda e to the negative lambda x. Okay, I did have it right, but you know. All right, so the PMF for the exponential. What follows an exponential distribution?
Waiting in line.
Waiting in line, exactly. So the number of people in line follows what distribution? Poisson distribution. Okay, so the number of people in line is a Poisson distribution. Your wait time for that line, it follows an exponential distribution. So depending on the lambda, there's always a possibility that you have 0 wait time, like you get to the line and no one's in front of you, okay? But because people arrive based on a Poisson distribution, there could be like 15 people in front of you or 3 people in front of you, right? And you know, if you were to do some kind of study at Ackerman, you know, that lambda changes throughout the day, right? During lunchtime, that lambda is like 500. Well, not really, but then and then at 9 p.m. it's assuming a place is still open. So like Carl's Jr. is still open at 9 p.m. and the wait time, the lambda there is going to be much smaller, right? So, okay, so here's our probability mass function, and our cumulative density function is 1 minus e to the negative lambda x, right? Okay, so we have 1 minus e to the negative lambda x, and let's just use it for lambda equals 1. Okay, with lambda equals 1, our exponential distribution looks like this. So for lambda equals 1, our PMF looks kind of like that. And then our CDF with a lambda equals 1 looks like this, the purple line. Okay, I should just copy this image, really. And it starts at 0 and it goes, technically this is asymptotic, right? And it just keeps getting closer and closer and closer to 0 as we get into infinity, right? Okay, and so the way we will do this is we're going to we will map. You can kind of just take this thing, and we're gonna what's going on? Okay, so we're gonna take this, and I'm gonna, can I stretch this? That's not, whatever. Okay, that's fine. And we're gonna say we're gonna generate from 0 to 1, from 0 to 1 here, and so the uniform U, everything between here and here is equally represented. Okay. So this is all equally likely. What is that? Okay, and then, this is 1, I think it's, so these are all equally likely, and this picture then provides a map. So we're going to basically just draw between 0 and 1, and what we do is, let's say I just randomly draw U, and can you guys see that? No, that's not a good color to use. Okay, let's say we draw U from uniform 0, 1, and let's say U happens to equal 0.2. Okay, so we end up right here at 0.2, and what this does is then say we map, we go right here to 0.2, and then it says, oh, we're going to be right here, and then we come across down to here, and we say, oh, now our x is going to be this value. Okay, so we're just basically we're generating on the interval 0 to 1, and this curve, this cumulative density function, provides a map to go from everything on the 0 to 1 to something in the domain of the x. Okay, so x goes from 0 to infinity, or x could go from negative infinity to positive infinity, and this just says if you get a particular u, then it gets mapped to this location on the x-axis. Okay, so is it possible to get a value of, let's say, 100? Yes, it's possible, and what has to happen then is that the u that we get has to be something like 0.99999. Okay, and when we do that, then this gets mapped all the way out to here, and when we do that, it gets mapped to, let's say, 100. Okay. So how does this work practically, okay? So if this is our cumulative density function, and the cumulative density function takes our x, the values of x from 0 to infinity, and maps it onto the space 0 to 1, right? The CDF maps from x to the space 0 to 1, right? So the maps from what we call the domain of x, which goes from in our case 0 to infinity, and it maps from 0 to infinity onto the space 0 to 1. This time we want to do the opposite. We want to go from 0, 1 onto this space of x. So to do that, we just take the inverse function. Okay, so we have to find the inverse function of the CDF, and so this is why it's called the inverse transform. We're going to take the inverse function of the CDF, and we're going to be able to go from 0 to 1 onto x. Oops. So in our scenario, so we want to go from the space 0, 1 to the space of x. Okay, in our case, 0 to infinity. Okay, and so our CDF again is 1 minus e to the negative lambda x, and we're going to we just want the inverse. To do this, we find the inverse of this function. So basically we just say, okay, I'm going to just call this u. U is equal to 1 minus e to the negative lambda x, or here, maybe just to avoid confusion, we can just call this, give me a letter here, g, okay? And then we want to find the inverse of this thing, and so we get e to the negative lambda x is equal to 1 minus g, and then we take the log of this, and we get negative lambda x is equal to the log of 1 minus g, and then we did I do something wrong? No, this is right. Okay, and then we get x is equal to negative 1 over lambda log of 1 minus g. Okay, and then so g here, we're going to say, again, g goes on the space 0 to 1, and so we're going to then replace this with a random draw from 0 to 1. Okay, so we'll just say g will be a random draw from 0 to 1. Okay, so technically 1 minus g is uniform 0, 1. If g is uniform 0, 1, 1 minus g is also uniform, right? Okay, and so we can then say x is equal to negative 1 over lambda log of what u is. Okay, and this is a way to generate random exponential values if starting with u being on the interval 0 to 1, we can then generate random values from the exponential distribution by finding the inverse of the cumulative density function. Okay, so all right, we'll end there, and we'll see you guys on Friday.